He is now the head of the machine learning and whatever group in Southampton, and before that he was a full professor at Royal Holloway College in London. And basically, I mean, he's probably one of the people who you would have encountered at some point anyway doing machine learning, statistical learning theory in Europe. So I mean, he's been around at least as long as I can remember, even though you don't look like it. And, okay, open stage for John. I mean, there'd be hardly any better to present this.
Okay, thanks very much. Thanks, Alex. Okay, and so thank you to the organizers for very honoured by this invitation to present at the summer school. So when I was asked to talk about basic statistical learning theory, I was trying to think what I could hope to do for you in this period of time allotted, and what you might be able to take away from this short set of lectures. And something that came to mind was a series of books that are actually sold in the UK, known as the Bluffer's Guide to. And you can get a Bluffer's Guide for all sorts of topics, from psychoanalysis to whiskey to skiing to philosophy or whatever. And the idea of a Bluffer's Guide, a bluffer is somebody who sort of makes his way by not really knowing what's going on, but has the right terminology and can sort of get by at the cocktail party. So the Bluffer's Guide book gives you all the key terms and tells you, how to use them in the right context. So, for instance, if you start talking in statistical learning theory about the ghost sample, you should know that that isn't the data set you used in your last NIPS submission. And the double sample trick is not actually something to do with cards, and so on. Concentration is not about the level of alcohol in your blood, and so on. So my intention there, I mean that's joking aside. I think these books actually also are quite instructive. I mean, they're surprisingly informative. They give you the sort of strategic level view of that subject that often is very hard to get from a textbook, which will go into a lot more detail and a lot more of the, you get lost in the detail and you don't get the sort of overview. So in a sense, that's the first level that I would like to try and reach, that people come away from this with a sense of what statistical learning theory is attempting to achieve, what is its sort of contribution, if you like, what does it bring to the table of machine learning, to what extent it's successful in doing that, and to what extent it fails or needs to be further refined. And I suppose, in a sense, putting it in the context of the research that you might be doing and how it relates to that research. So, if you like, that would be the level I would hope that everybody might take away from this. I think also I would, also hope that many of you might take a little bit more than that, in that I will hope to cover some of the key techniques, theorems, and ideas behind the theory in a way that I hope will enthuse you that there's actually a lot of interesting things in that theory and a lot of nice ideas that are fun to work with. So in a sense, I would like to hope that some of you will actually, feel, that's really interesting. That's something I, didn't know and now have learned about. And finally, also I might hope that many of you will take an inspiration from this to try and apply some of the ideas to the research that you're doing. So in a sense, that would be the major goal, would be to see that, yes, okay, that actually applies to what I'm doing. It can help me understand or further illuminate the actual algorithms I'm working with, the techniques that I'm using in my research, and actually those techniques could be applied in that area. So if you like, those are the sort of three levels I'm striving for. But certainly, I don't want to get lost in a lot of detail, and I want to try and give you some of the enthusiasm for some of the key ideas. So on that note, I'll move forward and give you an overview of the basic structure that the things I'm hoping to cover. So first of all, setting the context clearly. Statistical learning theory is something I'll need to put in context with other attempts to understand learning systems. So I'll spend most of this lecture looking at that. Then I'll move into the basic PAC ideas, probably approximately correct, is what the acronym stands for, and their proofs. And again, here I will be looking at some of the detailed proofs because I don't want to just give you a series of results. I want to try and show you how those results are arrived at, where the proofs are instructive in themselves. So it is my intention to try and look at proofs and see how they work, at least the key ideas of how they work. So I'll be looking at those in a little bit more detail. That will lead us to the sort of point at which, if you like, learning theory was at when suddenly support vector machines broke on the scene and were performing extremely well, and the theory that was at that point developed was completely unable to explain their performance. And I think that was a critical moment where, if you like, theory and practice were completely at odds with each other. And I think that was a challenge to the theory community to try and, if you like, upgrade their theory to match practice. And that's what I'll talk about next, which is this idea of real-valued function classes and the margin. That will hopefully be the point I reach at the end of today. So that's will be 4 lectures. And then, starting tomorrow, we'll look at more modern approaches in statistical learning theory, concentration and stability, and then Rademacher complexity and its main theorem, and onto some applications. So again, I would hope to cover, I'll go to the next slide now and give a sort of aim of what I would hope. In a sense, this is just giving a recapitulation to some extent of what I said at the beginning, but some thoughts on why theory, what it can do for you. The basic techniques with some deference to history, but not a strict historical sequence. Insights into the proof techniques and statistical learning approaches. And tomorrow, a complete proof of the SVM bound using the Rademacher approach. I think somehow taking you through the whole thing, it's like climbing Everest or something. It's not that hard. But it can give you an idea of what the different components that are needed in a proof are. Okay, so that is what I'm hoping to include. What I won't include is the most general results by any stretch. I certainly don't know them. I certainly won't include a complete history. I won't be looking at an analysis of Bayesian inference. Typically that is viewed as outside statistical learning theory until recently, when the development of the PAC-Bayes approach, which sort of links the two, but I again won't be covering that. And Olivier Bousquet, who's giving the advanced section of this course, will be looking at the PAC-Bayes results. And also at this idea of local Rademacher complexity, so developing on from the Rademacher stuff I'll be talking about tomorrow. Okay, so let's hopefully set the scene. I would welcome you to ask questions and again give feedback about speed and appropriateness of what I'm saying. So please just throw up your hand and I'll try and spot you. Okay. So I'm going to start with an attempt to... by the way, is there a pointer that I can use for the... just that, I see. Okay. Right. Okay, so I'm going to start with, if you like, how does the statistical learning community approach what they're trying to do in understanding learning systems? So the basic viewpoint is a statistical one, clearly, as the title suggests. But as with any theory, the aim is to try and model some phenomenon. And in this case, it's part real, part artificial. The data may be real, but the actual algorithms are artificial. But it is a phenomenon. And you're trying to understand what's going on. It's the nature of science is exactly this. You have some phenomenon in the world, and you try and write down a theory which explains that behavior of that system. And the aim, of course, of doing that is in one sense just the intellectual enjoyment of having an understanding of the world. But the more practical approach is in order that you can predict how that will perform and hopefully get it to perform better. That is, exploit your knowledge in terms of actually improving the algorithm, improving whatever you're trying to do. So a theory is always there to try and support practice. And there's always this interleaving between theory and practice, and the more active that interleaving, the better, I think, for both, for the theory and for the practice. I should emphasize right away, statistical learning theory is just one approach to understanding these learning systems. And other approaches include Bayesian inference. As I said, I'm not going to speak about that. Inductive inference, statistical physics, traditional statistical analysis. All of these have perhaps slightly different emphases and different premises in the way they approach and different strengths. So I'll mention that on the next slide. Each theory makes assumptions about the phenomenon of learning. So if you're trying to model something, your immediate task is to abstract away from the details of the particular into a level that you can actually make some conclusions and derive some results about. And in that abstraction, you're going to lose something, for sure. And the critical thing is to choose your modeling at a level that captures the essential and doesn't lose critical elements of the thing you're studying. If you abstract too far, you may get a beautiful theory, but it'll no longer be applicable. And each theory abstracts in its own way. And so, to say one theory is better than another is always a very risky thing to say. I think it's a case of looking at, one theory may be more applicable in these type of situations because the abstraction it makes is appropriate and captures what's going on in that situation. This theory may be more appropriate in this situation where the actual conditions are slightly different. So I think, to sort of get into turf wars about Bayesian and frequentist statistics seems to me very short-sighted, and really what we should be trying to do is understand when one works and when the other works. So on that note, I think that hopefully as part of this course one will begin to see what the modeling that statistical learning theory does contributes and where it can be of use. And I certainly don't want to make a claim that it's the be-all and end-all of understanding learning by any stretch of the imagination, but hopefully it has something to bring to the table of this very interesting subject. Okay. So now getting into a little bit more down into the particular approach of statistical approach to learning. I'm going to simplify at this point, but I think it's setting a framework that will be very generally applicable in this approach. The assumption that you typically begin with is that the data is generated by an underlying distribution. So it's a sort of probabilistic assumption about the way the data arises. And that the learner himself actually has very little access to information about that distribution. He may have some prior knowledge, but not enough to do what a Bayesian would do, which is build a model of that process. So you're making the assumption that you have very little knowledge about the way the data is generated. For instance, if we are trying to classify tissue samples to decide whether they are cancer cells or not cancer cells, there is a distribution of the way those cells look from a particular population. So a typical healthy cell looks in this sort of way, and if you generate a typical healthy cell, you'll get an example of that probability distribution. Typical cancerous cells look this way, and if you generate one from the probability distribution of cancerous cells, you get an example of that distribution. So this is the assumption behind. Now, of course, this is already making maybe some too strong steps, and of course this is, as soon as you make these assumptions, you may lose something, and that's the price you pay for making a theory. But that's the approach that's taken. In a sense, this assumption of a distribution subsumes everything that we might hope to know about the processes in the natural artificial world that we are studying. Now, that's not going to be true in the end, because we're going to make, in the way we design our learning algorithms and so on, we're going to incorporate our knowledge about the world, the problem we're studying. But in a sense, the distribution contains all the real information. Now, the problem in learning is precisely the fact that that distribution contains the information, but we have no way of accessing it directly. We have no way of getting to, if you like, an explicit formula for the probability density function of that distribution. Rather than that, we're given a rather poor training sample or training set, which is just a sample of points generated according to that distribution, the classical situation, the training sample. Now, I've given an example here with a input-output pairing. I'm probably going to focus mainly in this course on classification. So one would think of the Y's as being a label indicating membership of a class or not. But of course, in general, they could be real-valued outputs, or they could be vector-valued outputs, or they could be it could be just no output and just a clustering problem, for example, where you only have effectively an input to your system. But as an example, here we have the pairs, input, say classification output, x1, y1 up to xm, ym. And again, the assumption we're going to make, and again this is already making another assumption, is that this sample is generated independently and identically according to this distribution P. So in a sense, we're getting our information about P comes through this sample. It comes through independent generations of examples by that distribution. Okay? Now this leads very immediately to what we would then try and do. Typically a learning algorithm, and I'm using a curly A here, would choose a function from a function space f up here, and I'm denoting the function it chooses by the algorithm sub f applied to the training set S. So notice that the actual choice of function will depend on the training set. Even if you're learning the same problem, if you generate a different sample and apply your algorithm to it, it's going to give a different result. Hopefully not that different, but it will be different. So that's the sort of result of your learning algorithm. That's the actual function that it gives. And from a statistical point of view, the quantity that we're really interested in is this quantity here, which is the expected value of the loss when we apply this function to a randomly generated new test point. So xy is a new test point, and this is the function we learned from the sample which we were given. And when we apply that function to the new example, and according to some measure how well it matches the output, so the loss here is some measure of the fit, if you like, of the output of your function that you've learnt and the actual output that should be given. And we want really to estimate the expectation of that loss. And I'm going to call that epsilon S, A, and F. So this S is the sample. It depends on the particular sample now. This is the loss for a particular training set, an algorithm, and a function class. So this is, if you like, the measure of performance of the actual algorithm on the particular training set. So for example, in the case of classification, we can take the loss L to be 1 if the two disagree. In other words, if the output of your function applied to the test input is different from the output that should be given, so it gives the wrong classification, and otherwise to have 0 if it's the right classification. While for regression it could be the square of the difference between the output of the function, so this will now be a real value, and this will be the true output. Of course, this would be difficult to say it could be correct, so you typically, exact, it'll be only accurate to a certain degree, so you take the difference between these and square them, and the loss is not a discrete quantity in that case. So we're going to refer to this random variable, epsilon SAF, as the generalization of the learner. Okay, so it's a very, very core concept. So rather than, I think it might be worth doing a very little simple exercise at this point, just to sort of, before we lose ourselves in the symbols. So what I'd like you to do is find out another way of expressing this quantity in the case of classification. So as I've written it, it's the expectation of a loss. Okay, but in the case of classification, you can simplify that down to something perhaps more understandable. So if you just want to take a couple of minutes to try and write down what that would be in the case where the loss function is this discrete loss. 1 if you're misclassified, 0 if you get the right label. Okay. No one. Okay. Yeah. Okay. Yeah. Do you want to?
I'm not sure about you. I just wrote the sum from 1 to n of an indicator function, where the sign of the output of your algorithm or your function is equal to the target y you're looking for.
Yeah.
That's it.
Well, that's actually the test. Sorry, that's the training error, I guess, that you're thinking of there. What this is the test error. So it's more. That certainly would be the right estimation on the training set. But what I was looking for was an expression for this in terms of the probabilities of these events. Does anyone else have a? Yeah.
Is it the integral of the delta function?
It could be expressed in that way, that's for sure, yeah. I actually was thinking of well, let me show you what I was thinking, and then hopefully it'll be clear. So if we take that, I have to do this, and then that. If we take that expectation over xy of the loss of the function, I'll just write a of s, leaving out the f, x, y, okay. So essentially we can write that as the... Thank you. Okay. We can write that as the probability that the probability that as of x is equal to y times 0, because the loss is 0 in that case, plus the probability that as of x is not equal to y times 1, because the loss in that case, this is just working out the expectation in terms of the different events that can occur. Remember, the discrete loss is... This isn't perfectly focused, is it? Oh, okay. Can you see at the back? Is that okay? Yeah. Okay. So that means that, of course, this doesn't occur, and it actually just equals the probability that the function applied to the new test point is not equal to the correct value. So in other words, in this case, this generalization for the discrete loss is just the probability of misclassification. That's all I was trying to drive out. Maybe I didn't express it very clearly, but it's just in that case it becomes a very simple expression. Is everyone happy with that idea? Any questions? Okay. So I just don't want you to get fazed by all these. I mean, one of the big problems with theory is that because you have to write things down precisely, you get all of this sort of garbage of symbols. And it's just, I mean, once you get used to it, it's just a set of symbols. I mean, the ideas are not actually that difficult or complicated, really. It's just you get fazed by the symbols. So part of it is to just work with them a little bit and get familiar with the symbols and the way that they... So, this looks horrid, but in this case it just reduces to something very simple. Okay. So this is really a very, I think, important... I need to put this back. Right, sorry. So this quantity, epsilon SAF, this is the expected value of the loss on a randomly generated test point. In the case of classification, it's just the probability that a randomly generated point is misclassified. If you think of running your algorithm with a training and a test set, your test set error, which perhaps is also what you were referring to maybe, is an estimate of this. It's a sample estimate based on actually looking at the test examples, which you assume again are generated according to the same distribution. So it's a good estimate of that quantity. But from a theoretical point of view, we prefer to think of this as the quantity we're really interested in. It's the pure probability of misclassification of a randomly generated point. So I want to try and give an example of what this random variable, how it looks in a particular concrete case. Because I think if you can build up a picture in your mind of what this random variable distribution looks like, a lot of learning theory starts to make sense. You can see what learning theory is attempting to achieve. So I'm now going to give you an example, which is real-world data, breast cancer data set from the UCI repository. I'm going to do a very simple Parson window classifier as described by Bernard Schulkopf at the beginning of his lecture. So the weight vector is actually just, it's a linear function classifier, thresholded linear function. The weight vector is just the average of the positive training examples minus the average of the negative. So if you can imagine there's a cloud of positives, and you put a point in the center of that, there's a cloud of negatives, a point in the center of that, join the two and bisect the line between them. That is the hyperplane that we're going to use to classify. Okay, it's very, very simple. And what I'm going to look at is I'm going to repeatedly draw random training sets S, and I'm going to get an estimate of this distribution. I'm actually going to create a histogram of this distribution of the errors. So each time I draw a random training set, I'm going to compute this guy. Of course, I'm going to compute it in the way that we always do, estimating it on a test set. Okay, I can't help that, but because it's if you had some abstract problem where you could define the true error, but in our case we've got a concrete data set, so I'm just going to use the test error as a proxy for this. So I'm going to repeatedly generate random training sets, use the remainder of the data as a test set, and estimate this quantity after applying this very simple algorithm, the Parson window estimator. And I'm going to plot the histogram and the average of the distribution of this quantity for various sizes of training set. Now, if I take the whole data set, then that will give a single value, because essentially there's just one function, it's the average of the positives, average of the negatives, and I'm going to apply it to the same set. And it's just like a sort of, if you like, thing we might aim for, the best you could possibly do with this type of classifier in this situation. So I'm going to use that, if you like, as a starting point, the whole data set, and then I'm going to look at smaller and smaller values of training data. And we're going to look at what happens to the distribution in that situation. Is everyone clear what I'm trying to do? So I'm going to, say fix my size 342. That's half, actually, 50% of the training set. So I will then, train a Parson window on that half, test it on the other half, and I get one value of that error. And then I'm going to do that 1,000 times and get a histogram of the errors that I get out. Okay, and then I'll compute the average. Okay. The reason this is quite a interesting example is that actually the expected classifier that we get in all cases, whatever sample size we take, is the same, because the expected value of this, the result of this learning algorithm, is the expected value under the particular training set of the positive average of the positives, which I'm denoting W plus sub S, and the average of the negatives I'm denoting W minus sub S. And because the expectation is can go through addition, we can actually write this as the expectation of the positives minus the expectation of the negatives. And then we've got this is just actually the expectation of the points that have positive label. Because the average of a set of points of positive label, if you sample size whatever, you're always going to, the expected value is always going to be the true mean of all of the positives. So in fact, this, and this is going to be the true mean of all the negatives. So the expected value, of course, as you get small training sets, you're going to get lots of variation, but the expected value of this classifier is always the same. That doesn't actually mean that the expected loss, the average loss, is going to be always the same, because the loss is a nonlinear function, so you can't do this trick for the loss. But it does sort of give you a feeling that, the loss shouldn't change, the expected loss shouldn't change that much. And we'll see that is to some extent true. Okay. So here's the sort of perfect case where you take the whole training set. So essentially there's just one value. The distribution is a single point at about 0.14. That's the error of the Parson window estimator, if you like, on the whole data set. Okay, so now we're going to move to, say, size 342. So, of course, notice that the expected value is almost identical. So, as we predicted, the expected value is sort of pretty tight there. But now we're getting quite a bit of variation in the actual random values of this generalization. So on some training sets, we're getting errors as high as 0.2, and on some we're getting errors as low as 0.1. And it's just the luck of the game. If you happen to be lucky and get a good training set, or maybe you might say a good test set, it depends which way you want to look at it, then you actually get a better generalization. So now, as we reduce the size, the distribution begins to slightly change. So that's down to 0.4, 40% of the training data. That's 30% of the training data. 30% of the data for training, 20%. And now you can start to see that the distribution is beginning to get a little disheveled. We're starting, because the training set size is small, but notice that the mean is still very nicely centered where we started. Okay. And if we keep going, now we're already getting, quite a little bit of tail. We're getting errors as high as 0.3 on this. The mean started to move a little bit, but not very much. Okay, and if we keep going, that's down to, I can't remember what the percentage was, it's 34, 27, 20. And the mean is still below 0.2, so it's only increased by about 0.5, the mean. But, we're already getting errors as high as 0.6 up here on some training sets. Okay. I did make sure that the training set had the right proportion of positives and negatives, so I wasn't cheating. It's not bad because of that. It's just, bad luck in terms of statistics. So that's 14, and now we're getting errors right up there. And finally, that's, training set size 7. Okay. So clearly, hopefully from those you can start to see the way in which this distribution behaves. And the thing perhaps I wanted to emphasize particularly is the difference between the mean of the distribution, which actually kept to be quite nicely focused around the value you had at the optimum, in a sense, the start, and the actual spread of the distribution, which started to get to look quite bad. Okay. Now, traditional statistics has actually concentrated on looking at that mean. And typical sort of consideration is the consistency of an algorithm. And the consistency of a classification algorithm A is defined to be the property that the limit as m tends to infinity of this, so the sample size is tending to infinity, the expected value of this distribution of errors tends to what's known as the Bayes optimal function. The Bayes optimal function is essentially the best you could ever do in a classification algorithm because it simply classifies according to the label that is more likely. So it covers the case where you might have noise in your data set so that a particular example might in some cases be classified both positively and negatively with different probabilities, and in that case obviously you have to pick the label that's most likely, and that's what the Bayes thing does. Yes?
So slightly confused. Do you have on one side the limits as the sample size approaches infinity of an expectation of a generalization error?
This should be the generalization of the Bayes. Sorry, that you're right. Yeah, sorry, that should be the loss of the Bayes, expected loss of the Bayes function on this side. Thank you. Well spotted. Everyone see that? Yeah. You might want to add that. So this should say the expected value of the loss of f Bayes on xy. So what I meant was that the function essentially converges to, or you could just say the limit as m tends to infinity of as of f is f Bayes. So that's the sort of the study. But I think from the previous slides you can see that the problem with n tends to infinity is that it's as long as a piece of string. Does it happen at 1 million? Does it happen as 1 billion? There's what we want to know is what happens on a finite sample, really. For a finite sample generalization, has a distribution depending on the algorithm, function class, and sample size. So, as I've indicated above, the traditional statistics has looked at the mean of this distribution, but I think we hopefully have seen that it can be misleading. And low-fold cross-validation is another example where you can prove properties about the expected value of cross-validation that are very nice, but obviously in practice you can see that if you take a low-fold cross-validation you can get quite serious errors in what you do, and that's due to this variance in the actual value. So what statistical learning theory has preferred to analyze is the tail of the distribution. So rather than look for that mean of that distribution, it's focused in to try and estimate, if you like, worst case, but how far out you might go, provided you're willing to throw away a certain amount of probability. So let me go back to one of those pictures, and I think it should be clear. So what you might say in statistical learning theory is you want a bound that says, okay, I'm willing to accept that 1 in 1,000 or 1 in 100 times I'm going to completely mess up. I'll just be unlucky. My training set will just be so weird that I won't be able to learn. But I want to be 99% confident that I'm going to have an error better than something. So if we take that example here, what we would say, I mean, this is actually 1,000 simulations. So if we cut off the top 10, the best we could say would be something like about 0.65. So you imagine, we're allowing ourselves the luxury of throwing away the tail of 10 sort of worst case runs, and then what is the worst error we can get? 0.65. So this is the kind of estimate that we might expect from a statistical learning analysis, and clearly there's a very big difference between that and the expected value, which is still down way in the below 0.3. Similarly, if we go back one more, maybe the top 10 here might bring us to about 0.5, but the expected value is still well close to the true value, 0.2, 0.14. So you can see that there's a very great difference in what you're actually doing in some concrete cases. So in a way we can see it a bit like a statistical test. If we're significant at the 1% confidence, that means in a statistical test, that means that the chances that data arose if the hypothesis is true, I hope I got that the right way around, is less than 1%. And so you throw out the hypothesis. You say that, okay, I may be wrong 1% of the time I will be, but the chances of that data arriving if this hypothesis was true is so low that I'm going to assume the hypothesis is false. Here we've essentially got the same thing. We've got, we affirm that the generalization error is less than something. Of course, there's a chance that we might be wrong, that the data set was so misleading that we actually made that mistake. And this actually is the source of the acronym PAC, which stands for probably approximately correct, and the confidence parameter delta is this probably bit, which is this confidence. So it's the chance that we were misled by the training set in our calculations. So we say probably in the sense that with probability 1 minus delta is the probability that, okay, we were just unlucky and we got a really bad training set. Probability 1 minus delta is the probably part, and approximately correct is the generalization error part, the actual value of the generalization. Okay, so how are we doing for... so I think I would like to try and just do this slide if we can. I'm sort of got 1 minute. Well, I'll start doing this slide anyway. So one of the things I wanted to try, as I said at the beginning, to do is to sort of give you the flavor of the key approaches that statistical learning theory uses. And one of the sort of key ideas when you're applying this is to aim to bound that value delta. So you try, when you're trying to work out a sort of bound on the probabilities of these things, you aim at bounding the probability that will then be set equal to delta. So for instance, and that is this probability essentially of being misled. So let's take a very, very simple case of a single bad function f. So this is a function that has a bad generalization error has error greater than epsilon, where epsilon is some number which we won't specify at the moment, but let's say 0.1 or something, but actually looks good. It has 0 training error. So I'm denoting error sub s as the training error, and error, the sort of generalization error that we're looking at, the actual error on true probability error. So what we try and do is bound the probability that a sample will actually make f look this good when actually it's not. Okay, so this is the idea. You're sort of approaching it to bound over a sample that it can mislead you. Okay, so how would this look? It's the probability that the training error is 0, the true error is epsilon. Now we use the fact that the sample is generated independently at random according to the distribution. So as we generate the first example, the chance that it looked good was, of course, 1 minus the error of f. Right? The error of f is the chance of a randomly chosen example being misclassified by f. So in order for it to look good, it has to be correctly classified. So it has a probability of 1 minus the error of f. Okay? And because of the independence, the probabilities multiply up. So the probability that m examples mislead us, independently chosen, is that probability 1 minus error of f to the power m. And because error of f is greater than epsilon, this is less than or equal to 1 minus epsilon to the m. So we've just slightly reduced this value here, which has increased this value. And now there's a step here from this expression to this expression, which is very sort of often used. 1 minus epsilon, we could imagine, again, making it a bit bigger by expanding it by plus epsilon squared over 2 factorial minus epsilon cubed over 3 factorial plus epsilon to the 4th over 4 factorial and so on. And that would make it slightly bigger. And that actually is the expansion of e to the minus epsilon. So we get e to the minus epsilon to the power m, which is the e to the minus epsilon m. Okay, so it's just a very standard little approximation that we make. So what we have is that the probability of this guy misleading us with that it looks very good on the training set but actually has some error is getting to be exponentially small as the training set size increases. Okay. So at that point I think I'll take a break, but if you in the break are looking to have some fun, you might want to try and derive this quantity by setting this equal to t. So this is saying, let's say we want this value to be equal to t. What value of epsilon should we choose to make this equal to t? And this is the value. So you might want to just have a little look at that. Okay. So I think how long do we have? Quarter of an hour? Quarter of an hour. Okay. So we meet back at, let's make it 10 if we can. Okay. A little maybe 2 minutes after. Thanks.